Not long ago, a study published in the monthly notices of the Royal Astronomical Society letters caused quite a stir in the scientific community. The research, led by Professor David Wiltshire from the University of Canterbury, analyzed an extensive dataset of over 1,500 Type 1a supernovae and presented a controversial claim. The accelerating expansion of the universe might not be real at all, but instead an illusion caused by the way we measure time and distance. If true, this would mean that dark energy, an unknown force thought to make up nearly 70% of the universe's energy density, does not actually exist. This isn't the first time such an idea has been proposed. Many alternative cosmological models have attempted to challenge the standard view, but few have gained serious traction. However, this study has successfully passed peer review and presents compelling evidence based on new high-precision data from the Pantheon Plus supernova catalog. It suggests that our conventional understanding of cosmic expansion, based on the Lambda cold dark matter model, might need a fundamental revision. Of course, the claim is controversial. The Lambda-CDM model is the foundation of modern cosmology, supported by decades of observational data, including measurements from the Hubble Space Telescope, the Planck satellite, and the Dark Energy Survey. If dark energy does not exist, then something else must be responsible for the apparent acceleration of cosmic expansion. This study proposes that the key lies in the Timescape Cosmology framework, which suggests that variations in gravitational effects across the large-scale structure of the universe distort our perception of time, creating the illusion of acceleration. This raises a major question. Could our understanding of the cosmos be fundamentally flawed? And if so, what does that mean for the future of astrophysics? Let's take a closer look at the scientific battle between the Lambda-CDM model and this emerging Timescape model, and explore what it means for our place in the universe. The Lambda-CDM model, also known as the Lambda cold dark matter model, has been the cornerstone of modern cosmology for decades. It describes a universe composed of ordinary matter, cold dark matter, and the mysterious dark energy that drives cosmic acceleration. But how did scientists arrive at this model in the first place? In 1929, Edwin Hubble made a groundbreaking discovery. Galaxies are moving away from us, and their recession speed is proportional to their distance. This relationship, now known as Hubble's law, provided the first observational evidence that the universe is expanding. However, the idea had already been theoretically predicted in 1927 by Georges Lemaître, a Belgian physicist and priest, who derived it from Einstein's general relativity. This revelation changed everything. It confirmed that the universe was not static, as many had assumed, but was instead evolving over time. Scientists soon realized that if the universe is expanding now, it must have originated from a single, incredibly dense and hot state, a concept that laid the foundation for the Big Bang theory. With this understanding, the next major question emerged: how will the universe evolve in the future? Would it continue expanding indefinitely, slow down, or eventually collapse under its own gravity? This debate lasted for decades, with many astronomers believing that the expansion was simply an aftereffect of the Big Bang and would gradually decelerate due to the gravitational pull of all matter in the universe. Then, in the late 20th century, a new twist in the story would change our perception of the cosmos forever. In 1998, two independent research teams, the Supernova Cosmology project led by Saul Perlmutter and the Heisey Supernova Search team led by Adam Rees and Brian Schmidt, made a shocking discovery. By studying distant Type 1a supernovae, they found that these exploding stars appeared dimmer than expected. This meant they were farther away than they should be if the universe's expansion was slowing down. The only explanation was that the universe's expansion wasn't just continuing, it was accelerating. This unexpected result led to the introduction of dark energy, a mysterious force that seemed to counteract gravity and drive cosmic acceleration. Scientists proposed that dark energy was a fundamental component of the universe, making up roughly 70% of its total energy density. The cosmological constant, which Einstein had originally introduced and later abandoned in his field equations, was revived to account for this repulsive force. But where was this energy coming from? Physicists explored multiple explanations, including modifications to general relativity and the possibility of an unknown quantum field permeating space. Some even proposed a new form of gravity that wouldn't require dark energy at all. However, rewriting gravity was no small task. Tweaking Einstein's equations risked creating more problems than it solved, requiring an entirely new framework for cosmology. To avoid dismantling the entire structure of modern physics, scientists took the simpler route. They incorporated dark energy into the existing model as a placeholder for whatever was driving acceleration. Thus, the Lambda-CDM model was solidified as the standard framework of cosmology. For years, observations continued to support this model. However, some inconsistencies, like the Hubble tension, where different measurements of the universe's expansion rate yielded conflicting results, suggested that the story might not be as straightforward as it seemed. And now, new research is challenging the very foundation of this understanding. For decades, multiple lines of evidence have reinforced the idea that dark energy is real. One of the most significant pieces of evidence comes from observations of the cosmic microwave background, the faint glow of radiation left over from the Big Bang. Data from missions like NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite have provided highly precise measurements of the CMB, showing that the large-scale structure of the universe aligns with the predictions of the Lambda-CDM model, which requires dark energy to explain the observed expansion. Another crucial clue comes from the integrated Sachs-Wolf effect, which links dark energy to the way galaxies are distributed across the universe. This effect describes how CMB photons gain energy when passing through large cosmic structures, such as galaxy clusters. If dark energy were not present, these interactions wouldn't match observations. Studies of galaxy surveys, including those from the Sloan Digital Sky Survey, have found clear evidence that the ISW effect exists, supporting the presence of dark energy. Additionally, measurements of baryon acoustic oscillations, BAO, ripples in the density of galaxies left over from the early universe, serve as another independent check. Large-scale surveys, such as the Dark Energy Spectroscopic Instrument and the BOSS experiment, have mapped these structures in incredible detail, and their findings are consistent with a universe that includes dark energy. Taken together, these independent lines of evidence, supernova observations, the CMB, the ISW effect, and BAO, have built a strong case for the existence of dark energy. However, the nature of this force remains a mystery. Could these observations be explained in a different way? This is where alternative models, like Timescape Cosmology, enter the conversation. The Timescape Cosmology model, first proposed by David Wiltshire in 2007, presents a radically different way of understanding cosmic expansion. Instead of assuming that the universe expands uniformly like a well-risen loaf of bread, this model suggests that the universe is more like Swiss cheese, filled with enormous voids separated by denser regions of galaxies. These vast cosmic voids, some stretching over 2.5 billion light-years, contain much less matter than galaxy clusters, leading to significantly weaker gravitational fields. According to general relativity, gravity affects not just the motion of objects, but also the passage of time. The stronger the gravitational field, the slower time flows. In a universe dominated by massive voids, clocks inside those regions tick faster than clocks within galaxy clusters. This difference in time perception, according to the Timescape model, could create the illusion of an accelerating universe. In this framework, the apparent acceleration seen in Type 1a supernovae isn't due to dark energy, but rather a calibration error in how we measure cosmic distances. The model argues that our calculations fail to account for time dilation effects caused by variations in gravitational potential. If this interpretation is correct, then the need for dark energy disappears entirely. While intriguing, the Timescape model faces a steep challenge. It must not only explain supernova data better than the Lambda-CDM model, but also account for cosmic microwave background radiation, galaxy clustering, and large-scale structure formation. Some studies have suggested that Timescape Cosmology provides a slightly better fit to certain supernova observations, but whether it can completely replace the standard model remains an open question. One of the key arguments behind Timescape Cosmology is the role of time dilation in shaping our perception of the universe. According to Einstein's general relativity, time flows at different rates depending on the strength of the surrounding gravitational field. The stronger the gravity, the slower time moves. This effect has been confirmed through atomic clock experiments on Earth, and even observed in extreme environments like black holes, where time nearly freezes at the event horizon. According to David Wiltshire's calculations, a clock placed inside one of these vast voids would tick 38% faster than a clock in a high-density region like the Milky Way. If astronomers fail to account for this difference when measuring cosmic expansion, they could misinterpret the data, mistaking a variation in time flow for accelerated expansion. This concept provides an alternative explanation for the supernova distance problem, the very observation that led to the discovery of dark energy. In the Timescape model, the dimming of Type 1a supernovae is not due to acceleration, but rather the fact that we are observing these explosions from regions where time moves more slowly. The farther away we look, the more voids dominate our view, amplifying this effect and creating an illusion of acceleration. To test whether timescape cosmology provides a better explanation for cosmic expansion than Lambda-CDM, researchers analyzed data from over 1,500 Type 1a supernovae using the Pantheon Plus dataset. This massive collection of supernovae, compiled by the Harvard-Smithsonian Center for Astrophysics, serves as one of the most comprehensive tools for studying cosmic expansion. The results were surprising. When comparing the statistical fit of both models, the Timescape model showed a stronger agreement with supernova data at lower redshifts. The analysis used a Bayesian evidence test, a method that directly compares how well different models fit observational data. The numbers indicated that Timescape performed better at explaining nearby supernovae, while at greater distances, the difference between the models became less pronounced. This suggests that at local scales, the effects of inhomogeneity, such as the influence of cosmic voids, may play a bigger role than previously thought. However, the data also showed that at higher redshifts, neither model had a clear advantage, and in some cases, the Lambda-CDM model still performed competitively. Another key limitation was the redshift range used in the study. The supernova method is most effective up to distances of around 10 billion light-years, but the observable universe extends to 46.5 billion light-years. This means that beyond a certain distance, the data becomes sparse, and the ability to distinguish between models weakens. To truly test whether timescape cosmology can replace dark energy, additional data from other sources, such as cosmic microwave background radiation and baryon acoustic oscillations, is needed. Additionally, the structure of the early universe poses another problem. At high redshifts, we observe the universe in its younger stages, before large cosmic voids had fully formed. If the timescape model were correct, its effects should be less prominent at those distances, yet current data does not clearly support this expectation. To address these issues, scientists are looking toward next-generation telescopes. The Vera C. Rubin Observatory, set to conduct the legacy survey of space and time, will gather an unprecedented number of high redshift supernovae, providing a better test of timescape predictions. Meanwhile, the Nancy Grace Roman Space Telescope, launching in the late 2020s, will further refine measurements of cosmic expansion and dark energy properties. The Lambda-CDM model has been the dominant framework of modern cosmology for decades, successfully explaining a vast range of observations, from the cosmic microwave background radiation to the large-scale structure of the universe. While the timescape model challenges the need for dark energy, it has yet to demonstrate that it can fully replace the standard model on all observational fronts. The recent study supporting timescape cosmology provides valuable insight into the effects of inhomogeneity and cosmic expansion, but it does not conclusively disprove dark energy. Instead, it highlights potential gaps in our understanding and suggests that non-uniform expansion might play a greater role than previously assumed. Whether dark energy is truly real or just a cosmic illusion remains an open question, but for now, the Lambda-CDM model still stands as the best explanation for the universe's accelerating expansion.